Welcome to the presentation on Poseidon OS, an innovative open source storage system and its exploration using Trident. I am Badarinarayan Joshi. I work at Samsung Semiconductor India Research Facility at Bengaluru. In this talk, we'll take you through following topics: NVMe-oF interface, disaggregated architecture, vital virtue of any NVMe-oF solution. We will introduce you to the Poseidon project, the software component of it, its architecture, performance, open sourcing part of it. We'll also introduce you to the test tool which can be used to explore the Poseidon OS, how it can be configured and set up onto uh, any lab setups. Let's begin with introduction to Poseidon OS. Before going to the Poseidon OS, we can have a look at the NVMe over the Fabric interface. NVMe-oF has emerged to break through the scaling limitations of PCIe attached NVMe. It allows storage applications to talk to remote NVMe devices over network and consequently unblocks those applications from the physical limitations on the number of PCIe lanes a single host can have. It performs encapsulation and decapsulation at each layer of the software stack to maintain end-to-end NVMe semantic across a range of topology. In this illustration, you can see that how NVMe command traverses from host to the SSDs connected onto the server via NVMe over Fabric network. When we compare disaggregated architecture with the direct attached architecture, we see one major issue with the direct attached architecture, which is scalability. Also, the total cost of ownership, as the NVMe SSDs are costly and have to be maintained on premises. NVMe-oF interface brings independent scaling of storage resources by means of disaggregated architecture, where CPU and storage can be segregated into compute and storage interfaces. Storage comes over network with the NVMe-oF interface. This helps in increase the CPU and SSD utilization, reduces storage spending and total cost of ownership. It simplifies the scalability, provides high performance at lower latencies, increased hardware flexibility, and also it helps us achieve ideal capacity utilization. Let's have a look at what vital virtues of NVMe-oF solution. Any NVMe-oF solution is supposed to provide ultimate and stable performance for resource sharing. It is expected to give high availability for petabyte scale capacity, meta management for storage features at petabyte scale is supposed to be efficient. Optimized CPU, memory, and network resource utilization is also expected. Let's introduce you to the Poseidon project. Poseidon project is an open source hardware and software project basically introduced to expand the NVMe ecosystem. It is a OCP based collaboration between Samsung, Inspur, and Neighbor Cloud Technologies. Inspur is a server technology giant from China, whereas Neighbor Cloud is a cloud giant from South Korea. It is equivalent to the Google Cloud in South Korea. The software part of Poseidon OS is maintained in GitHub as an open source project, whereas the hardware from Inspur is available, which is compliant with the OCP specification. It supports a composable architecture based upon the SSD form factors, enabling storage disaggregation using NVMe-oF protocol. Poseidon OS is the software part of Poseidon project. It provides customized virtual devices to initiator via NVMe over the Fabric interface. Poseidon OS is a user space storage operating system for NVMe over the fabric. It provides a PCIe Gen 4 performance via network up to 200 GBE. It supports valuable storage features such as NUMA awareness, volume management, performance throttling at volume level. All the SSDs are managed as a RAID array, hence error management is also possible. And data is available even when SSD's failure happens, as part of the fault tolerance of RAID. Data is available all the time. Goal is also to provide a two-node high availability feature into Poseidon OS. It can also be consumed by the upper orchestration layers by means of RESTful APIs and also the CSI driver. Let's have a look at the Poseidon hardware. This is the version 1 of Poseidon OS hardware, which is compliant with the OCP specifications. This is manufactured by Inspur in this collaboration. So it basically has a chassis of EIA standard 19-inch one. The form factor is 1U. It has two processors, Intel next generation processors. The maximum number of memory slots is 32. It provides both RDMA as well as TCP data networks. PCI Gen 4 support is available, and SSDs connected in this server are of the form factor E1.S. 32 SSDs can be connected over it. The right side of the figure shows the inside details of the Inspur server. If you look at the goals of this Poseidon OS project is providing high performance at volume level for each of the clients. One target can be connected with multiple clients. So highest performance is supposed to be provided at each volume, which can be accessed from the clients. Quality of service is provided in the form of stable performance at each client. Since all the SSDs are managed as RAID and also two-node high availabilities will be provided, data is guaranteed from even the software and hardware errors. The main maintenance of Poseidon OS can be done using the CLI commands, also with the use of RESTful APIs. Let's have a look at the Poseidon OS architecture. Basically, there are three main modules in Poseidon OS. Storage resource management module handles all the fault tolerance, partition management at system user and meta area part. It has SSD management, which is the fundamental storage for the Poseidon OS, and all the physical device management is done by the storage resource management module. There is a metadata module. It contains the meta journaling file system, meta storage subsystem, and journaling. So in case of sudden power offs or normal power off and on of the system, the journaling and the metadata module enables recovering the array which is created when the system was brought up. There is a IO module, and IO module consists of mapper, allocator, volume manager, garbage collection, quality of service providing, NVMe-oF interfaces, IO scheduler, and CLI interface. Coming to the Poseidon performance part, we have achieved up to 200 GBE performance via NVMe TCP. The performance numbers are measured with user space driver, where clients connect to the target using NVMe CLI, and then FIO is used along with the IO engine, SPDK IO engine. And when the performance is measured, the sequential read write, we could see 24 Gbps and 22 Gbps values, whereas the random operations, we got 5.75 million IOPS and 5 million IOPS for read and write respectively. The same numbers when measured with kernel driver, that is the libaio FIO engine, we could see 23% drop in the performance numbers. This is expected as user space driver bypasses the Linux block layer, waits for the completion by polling for it, and hence achieves higher numbers with performance. Poseidon OS is available at GitHub in the following location. Users can download source code from GitHub and explore it by installing it on their commodity hardware or on the virtual machines as well. To help in with the documentation, there is another dedicated website made available, which is known as PoseidonOS.io. This website has blogs and technical material that can be used to explore Poseidon OS. Along with this documentation, test tool is also provided in the same repository, github.com and Poseidon OS, which is known as Trident. Trident is a Python test framework developed to explore and test Poseidon OS. Let's look into the design utility of Trident. Before getting into the Trident tool, we need to see what is the need for a test tool. If you see the configurations required for the Poseidon OS, the possibilities are innumerable. We can create a data array by using minimum 4 NVMe SSDs up to 32 SSDs. We can create multiple types of RAID arrays. Supported are RAID 0, RAID 5, RAID 10. In future, RAID 6 will also be supported. We can create single array, dual array, and create volumes into specific arrays and then execute IO on it. Subsystems and volume mapping has more possibilities, where you can create multiple subsystems and mount volumes across the subsystems. And data write onto the SSDs can be done with write through and write back mode. There are some features like journaling, telemetry, and QoS that can be toggled. Like you can enable journaling and then execute IO, or you can do it by disabling it. If you look into the client side possibilities, the exposed in volume at the client is seen as a block device that can also be mounted with Linux file systems. So, and multiple clients can connect to any given target with a single subsystem or multiple subsystems and run parallel IOs. If you look into these level of configurations, many possible test scenarios come out of it. To help customers and users exercise all these configurations, we have developed a test tool in Python. So let's look into the capabilities and usage of Trident. The first and foremost requirement from Trident is to validate the lab setup. So user, when he downloads the Poseidon OS, builds it, then to run the OS, he requires some prerequisites like the kernel version, the number of SSDs, which can be real SSDs or emulated NVMe devices, require specific size. Like minimum size of a SSD is 20 GB. All these validation has to be done to make sure that Poseidon OS is able to run on the given lab system. So that validation can be done by using a setup tool provided with Trident. And to test the Poseidon OS using Trident, the user need not have to have physical machines. They can work with QEMU and KVM. The Trident tool provides a configuration file that can be utilized to create many possible configurations of Poseidon, like array type and the number of arrays, number of volumes, and to begin the test, we need to be in particular stage. Like if we want to exercise volume operations, we can create array and start our test from there. So those configurations can be provided by using the config files given in the Trident test tool. Trident has a list of Python libraries developed. All these libraries utilize the Poseidon OS CLI commands. Also, other Python libraries such as Paramico, even FIO, all these are encapsulated into user libraries that can be utilized to create test scripts. Also, test scripts are provided with the tool, which exercise specific scenarios, like you need to run file IO with multiple initiator onto a target, and you need to exercise all the possible array states and multi-initiator scenarios. All those things, sample test cases provided that the user can utilize and even modify. Coming to the Trident architecture, the SUT, that is the system under test, is Ubuntu 18.04 server, which runs the Poseidon OS, and it has some utility services such as SSH server, NVMe TCP module, and user space device drivers. And this SUT need not be a physical machine; it can be a KEMU KVM virtual machine also. The framework layer has two parts: a library set and the scripts and configurations. Libraries are divided into two parts again. One is the system library such as Paramico, which is a Python module to work with SSH APIs. Threading library to execute IO in parallel. PyTest, which is a test framework which provides multiple features to write effective test cases. And concurrent module, again to execute IO parallelly. The other modules like POS, CLI, Node, Utils are written to exercise unique APIs. For example, CLI .py is a module which which implements all the Poseidon CLI commands. Poseidon CLI commands include array management, volume management, and so on and so forth. To create an array, to reset the arrays, to create volumes, mount volumes, rename volumes, all these are the CLI commands that are implemented in CLI.py. So user can call these core APIs to get things done. Similarly, Node.py deals with SSH related operations. Utils has utility operations such as FIO, calling the FIO and parsing its output. All those APIs are provided with the utils.py. Target utils has higher level APIs which exercise a set of core APIs to get one particular functionality done. For example, if a user needs to exercise normal power on reset, so that is defined as a API inside target utils, which calls the core APIs from other classes and get things done. There is a helper and logger module. Helper module has helper utility functions such as to create a random string and to get a Mellanox IP or a system IP. And logger module encapsulates the Python logging mechanism. Utilizing these libraries, test scripts are written in the scripts folder, so which has subfolders for various test cases. For example, array, volume, multiverse. Array is the folder which contains test cases related to array management, like array states and various array operations. And in volume folder, volume management related test cases are available. Multiverse is a folder which has test case which exercises multiple initiators talking to the target. Each initiator will execute a specific test case which runs for a longer duration. and there is a config file directory which hosts basically two configuration files. One is your topology file, and which has the IP address and other details required to communicate with the participant systems. And other config file is the Poseidon config, which talks about the nature of Poseidon system required for the test case, like whether you want one array, two array, all those details can be given in the Poseidon config file. Then there are other subsystem test cases and QoS test cases provided in respected folder. Coming to the configurations, as we talked about the topology.json has IP address and Poseidon OS installation directory path listed in it. Multiple initiators can be listed, and one target can be listed in this file. The main parameters to be entered are IP address, username, password, and data IP. Data IP is the IP address required for the data communication, through which target and client exchange the data. Pos underscore config JSON, as we talked about, is having the system details, like if you are creating arrays. So each array will have specific number of devices, specific number of data devices, and spare device, rate type. All these parameters are supplied in pos config.json. Another set of JSON file is the test case specific JSONs. These are apart from our existing basic JSON files. So these JSONs are written for specific test case. They will involve parameters such as how many initiators are involved, how many targets are involved, what is the total runtime of a test case, and what all modules this particular test case calls. These kind of information can be kept in the test case specific JSON. Coming to the Trident test setup, as we discussed earlier, it comprises of libraries, test cases, JSON configs. All these form the test framework. PyTest is utilized as a base for writing the test cases, and PyTest provides decent HTML reporting, also the test logs. So as you can see in this pictorial representation, the participant systems are three. One is your Poseidon target, and second one is the Poseidon initiator, and the third machine would be your test execution machine, on which the Trident is hosted. Target and initiator are connected via a data network switch, which can be Mellanox or any other TCP switch. So test case are invoked from the test execution machine, and commands are issued via the SSH onto target as well as the initiator. Trident, along with the Poseidon OS, is hosted in GitHub in the same repository, Poseidon OS repository. We can see the Trident as well. All types of contributions are accepted in Trident, like users can report bugs, improve documentation, add and modify test cases and libraries. And once the modifications are done, users can raise pull request, which can be acknowledged and included in the next releases of the Trident open source test tool. For user information, maintainer ID is provided. So any type of queries can be sent over this mail ID, which will be answered by the maintainer. Thanks for listening to this tech talk. Thanks SNIA India for giving us the opportunity to present Poseidon OS and Trident in this platform. Thank you very much.